So we left it last time, yeah. So finally, what we get is, so these are the two bases. The dimensions, yeah, is two. Okay, let's look at another example. Example number 4. Example number 4. Find the eigenspaces of the matrix A corresponding to the eigen values lambda 1 and lambda 2, where we have our A to be equals to 3, -1, -2, and 4, and then lambda 1 equals to 2 and lambda 2 equals to 5. Lambda 2 equals to 5. So find the eigenspaces of the matrix corresponding to those. So you just do it the same way. So here, let's start from the first one where the eigenvalue is lambda 1, which is equals to 2. So the solution. So number 1, the eigenspace of A corresponding to the eigenvalue lambda 1 equals to 2. So let's start from the first one. So we just do the same way. So we need to get the solution of the set A minus I. So in this case, it is so it is lambda 1, and then I. This is a 2 by 2 matrix. X equals to 0 vector. Equals to 0 vector. Now, so A minus lambda 1 identity 2 by 2 matrix is equals to, so we have our A, which is 3, -1, -2, and 4, and then minus lambda 1 is 2, 1, 0, 0, 1, which is the same as 3, -1, -2, 4, and then minus 2, 0, 0, 2, which is equals to 3 minus 2 is 1, minus 1 minus 0 is -1, 2 minus 2 minus 0 is -2, 4 minus 2 is 2. So that is what we get. Now we want to get the solution here. So this is this one. So we want to get the values of x1 and x2. So we put this one in eigen augmented matrix form, which is now 1 minus 1, 2 minus 2, 2, and then we have 0, 0 here. So when we reduce this one, reduce completely, then what we get is 1 minus 1, 0, and then 0, 0, and then 0. So therefore, our basic variable is x1, and our free variable is x2. Is x2. Now, our final linear equation here is x1 minus x2 equals to 0. So x1 equals to x2, x1 equals to 2. So then our solution set. Solution set, which is x is equals to x1, x2, which is the same as in this case, this is x2 and our free variable, which is x2 there. Is x2, and therefore this is the same as x2 1 1 for any x2 for any x2. And so therefore this is now our basis. So that is our basis. So we can say the eigenspace A of A corresponding to lambda 1 equals to is the span of 1, 1. So the eigenspace of A corresponding to eigenvalue here to. Now, what about when lambda is equals to 5? So you do it the same way when lambda is equals to 5. So you just do it the same way when lambda is equals to 5. So in this case, we want to get the solution 3, -1, -2, 4. So when lambda 2 equals to 5 minus, so here it would be 5, 0, 0, and 5 there. And what you get here is 3 minus 5 is -2, -1, and then -2 minus 0 is -2, 4 minus 5 is -1. And then now we write this in augmented matrix form: -2, -1, -2, -1, and then 0, 0 here. So when we reduce this, reduce completely, then what we get is 1 over 2, 0, and then 0, 0, 0. So here our basic variable is equals to x1 and our free variable is equals to x2. So our new solution set, our new linear equation here will be x1 plus 1 over 2 x2 equals to 0. So x1 equals to -1 over 2 x2. So finally, our solution set x is equals to x1, x2 equals to -1 over 2 x2, and then our free variable, which is x2 there, which is the same as x2 -1 over 2, and then 1 there. So finally, the eigenvalue or the eigenspace of A corresponding to lambda 2 equals to 5 is a span -1 over 2, 1 is a span -1 over. So that is how we get X. Now, how can we plot this one geometrically? So how can we plot this geometrically? So let's look at the geometric interpretation. Geometric interpretation of this. So here we have our eigenvalues as 1, eigenspaces as 1 and 1, and we also have -1/2 and 1, -1/2. So we can plot this and we can put this one as x1 and here as our x2 or x2 or x2. So -1/2 and 1. So we can say this is -1 and then -2 and then it goes like that. And this is, let's say, 1 and 2 there. Okay. And then 1 and maybe 2 there. So 1 and 1. 1 and 1 is somewhere there. Okay. 1 and 1. And then, so in this case, any point along this line, yeah, any point along that line is where our lambda 1 is equals to 2. And when it is -1 and 1 and 1, so -1/2 and 1, which is there, then any point along here passing through there. Yeah. So any point along there is where lambda 2 equals to 5. So any point. So that is how we geometrically plot the eigenspaces. Any question? Okay, let's look at a theorem here, which we will not prove. You can look at it in your textbook. The eigenspaces or eigenvectors, sorry, the eigenvectors of an n by n matrix A corresponding to pairwise distinct eigenvalues are linearly independent. So when we have different kinds of eigenvalues, then the eigenvectors that we get for X, they are always linearly independent. They are always linearly independent. Another theorem, theorem 2.3. The scalar 0 is an eigenvalue of an n by n matrix A if and only if A is single. If and only if A is single. So if the matrix A has a determinant of 0, then the scalar 0 is an eigenvalue of that. So you don't have to determine the eigenvalue if the matrix is single. So the eigenvalue is always 0. So what you need to get is only the eigenvectors, the eigenvectors. So we can try prove this. So here, if the eigen, which is the lambda, if the lambda is equals to 0, if lambda is equals to 0, then our solution, which is a minus lambda, in this case, in of x equals to 0, will now be the same as a minus 0 in x, which is equals to 0, which is equals to 0. So if this is 0 here, then when you distribute x here, then what we get is ax equals to 0. Ax equals to 0. So in this case, if this ax equals to 0 has non-trivial solutions, then A is a singular matrix as non-trivial solution. So if it is non-trivial solution, then that means this A here is linearly dependent. So if it is linearly dependent, then the determinant is equals to 0. So for example, example number 4. If we are given the matrix, so without calculation, find the eigen value of the matrix. A equals to 1, 1, 1, 1, 1, 1, 1, 1, 1. A equals to 1, 1. So if you look at this matrix, yeah, so you can easily get it done, right? So if you look at this, so when you use the cofactors method, so you can close this and this, and then 1 and 1 minus 1 and 1, you get 0, right? Close this, 1 and 1, 1 and 1, you get 0. Close this one, 1 and 1, 1 and 1, you get 0. So the determinant there is what? Is 0. So what is the eigenvalue? This one is 0 without any calculation. So our lambda is equals to 0 without any. Now if our lambda is equals to 0, now let's get the what? The eigenvectors. So in this case, then it means that A minus 0 lambda, 0, and then I in this case, I3, x is equals to what? Is equals to 0. So therefore, it means that Ax is equals to 0. Ax is equals to 0. So what we need to just do is to solve this matrix. To solve this matrix, we get the values of x. So when we write this in augmented matrix form, then it is 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. And then we do what? We reduce completely. So when we reduce completely, then what we get is 1, 1, 1, and then 0, 0, 0, 0, 0, 0, 0, 0, 0. So that is what we get. So therefore, our basic variable is x1, and our free variable is x2 and x3. x2, x3. So then our new linear equation here is x1 plus x2 plus x3 equals to 0. So x1 equals to minus x2 minus x3 minus x2 x3. So then our solution set, which is x is equals to x1, x2, x3, which is equals to minus x2 minus x3. Our free variable here is x2, and also our free variable here is x3. So then this is equals to, we factor out x2, which is minus 1, 1, and then the last one is 0, plus x3, which is here is minus 1, here is 0, and then finally here is 1. There is 1. For what? For any x2 and x3. For any x2. So then negative 1, 1, and 0, and negative 1, 0, and 1 are linearly independent. So they are linearly independent. They are linearly independent. Eigenvectors of A. Eigenvectors of A. So therefore, these are what? So these are our eigenspaces. So these are our eigenspaces. Any question up to that? So we're done with 5.2. Now let's 5.1. Now let's go to 5.2. This is the characteristic polynomial. The characteristic polynomial. So we will start from the characteristic polynomial of a square matrix. Let's start from the characteristic polynomial of a square matrix. Now, here we can let A to be an n by n matrix. We let A to be an n by n matrix, and our lambda to be an eigenvalue. Our eigenvalue, yeah. Then, if we remember, we said AX equals to lambda what? Lambda x. So we said AX equals to lambda x. Then this is similar to AX minus lambda x equals to 0. Which is the same as A minus lambda, and then you put the identity and there, x equals to 0. So here, this solution of A minus lambda in will give us non-trivial solutions. So it will give us non-trivial solutions, if we remember. So if it is giving us the trivial solutions, then that is the values of x1, x2, up to n I equals to 0. So if it is giving us non-trivial solutions, then this a minus lambda in is non-singular. So it is non-singular. No, I'm lying to you guys. So this is equals to 0, right? So it is equals to 0. So since this one, the whole of this is not giving us trivial solutions, then this is singular. Actually, this is singular. A minus lambda in is singular. So if this is singular, then the determinant of A minus I lambda n is equals to 0. The determinant is equals to 0. So this is where now it is giving us the characteristic. Because at this point, then we'll be trying to get the solutions for lambda. So we'll be trying to get the solutions. So to get the solutions for lambda, then we need to get a determinant of this, and we equate lambda to 0. We equate to 0. So then this will lead us to this theorem, which is theorem 1.1, whereby if we let A to be an n by n matrix, then number one, phi of lambda is equals to determinant of A minus lambda in is called a characteristic polynomial of A. And number two, determinant of A minus lambda in equals to 0 is called the characteristic equation of A, the characteristic. So the degree of this characteristic equation here is the value of this n. So if it's a 3 by 3 matrix, then the degree of this characteristic equation will be, if it is a 4 by 4, then it will be 4. So if it's a 5 by 5, then it is 5. So that is the degree of the characteristic equation. So we can write the degree of the characteristic polynomial phi of lambda is equal to n. In our case, is equals to n. So let's look at example number 1. How can we get the characteristic equation and what is the characteristic? So let's start from the first one. So let's find example 1. Find the characteristic polynomial and all eigenvalues of the given matrix. So if we are given the matrix A to be equals to 5 minus 3 minus 4 and 3. So find the eigenvalues for the given matrix. So what you need to do first, you need to get a characteristic polynomial. And then now, from B here, we get the characteristic, you bring this one together, which you get a characteristic equation. Now, from there, then we are able to solve the quadratic equation, if it is a 2 by 2 matrix, or 3 by 3, or the other. So in this case, then since this is 2 by 2, then the degree of this characteristic polynomial will be 2. So here, we need to get, first of all, we need to get the phi of lambda, which is the same as determinant of A minus lambda, in this case, I2. Right. So that is first. So how should we get, first of all, how should we get A? So our A minus lambda I2 is equals to just the way we did previously, 5 minus 3 minus 4, and then 3. And then here, minus lambda multiplied by the identity, which is 1, 0, 0, and 1, which should give us 5 minus 3 minus 4, 3, minus lambda 0, 0, and then lambda. Okay. So now get the final matrix, which should be equals to 5 minus lambda, and then minus 3, and then minus 4, and then 3 minus lambda. So that is this matrix. Now we need to get a determinant here. We need to get a determinant of this matrix, which will give us what? So once we get, so our A minus lambda I is equals to 5 minus lambda minus 3, and then minus 4, 3 minus lambda. 3 minus lambda. So here we need to now get the determinant of A minus lambda I, which is the same as phi of lambda there, which is the same as getting the determinant of 5 minus lambda minus 3 minus 4, 3 minus lambda. So using the same way we did for getting the determinant of a 2 by 2 matrix, so 5 minus lambda multiplied by 3 minus lambda here, minus, so minus 4 minus 3 is 12, so minus 12. So that is our characteristic. So this is our characteristic polynomial. So you can open these brackets. When you open these brackets, so our characteristic polynomial is equals to this, and this is lambda square, and then 5, and this is 15. So 15 minus 12 is plus 3 there. And then we have 5 and lambda minus 5, 3, and this, which will be minus 8 lambda. So that is our characteristic. Characteristic polynomial. Now, our characteristic equation will now equate this one to 0. So our characteristic equation is now lambda or phi is equals to 0. So that is our characteristic equation. So therefore, 8 lambda plus 3 equals to 0. So that is our characteristic equation. So we need to get the values of lambda.
How do you know that phi lambda equals 0? The characteristic equation. We're having that's equal to 0.
How come we are equating it to 0? So we say this is say this is singular. Okay. The determinant of this one is equals to 0. So that is what we just know. So once this determinant is equals to 0, then this is singular. Okay? So that is singular. So we get the determinant here. This determinant, all of this determinant here is equals to 0. So finally, this will now be equals to 0. So we want to get the values of this number here. Okay? So we try to get this one. Now we need to solve this. And you remember, okay, you did intermediate algebra, then you're able to solve this. There are several methods of solving that. So what is a fast method? So the easiest method is I use the quadratic formula. So if you still remember the quadratic formula, then lambda equals to in this case, lambda equals to minus b plus or minus the square root of b square minus 4ac divided by 2a. If you still remember quadratic. So our a in this case equals to 1, our b equals to minus 8, and our c equals to 3. C equals to 3. Then if you substitute here, then our b is minus 8. So in this case, it will be 8 plus or minus the square root of 64 minus 4 multiplied by 1 multiplied by c is 3 divided by 2 multiplied by 1. So finally, you get 8 plus or minus the square root of 64 minus 12 is 52 divided by 2. Divided by 2. So the square root of 52. So 52 has the factors of 13 and 4. 13 and 4 is 52, right? Yep. So our lambda equals to 8 plus or minus. So when you factor out, when you get the square root of 4, you get 2. So it is 2, the square root of 13, all over 2. And then this is finally the same as 4 plus or minus and the root of 13. So quadratic equations. So finally, therefore, this is so the eigen values are lambda 1 equals to 4 plus the root of 13 and lambda 2 equals to 4 minus the root of 13. So those are how. So basically, if the degree here is like 2, so we'll know that we get 2 eigenvalues. So if the degree here is 3, then we should get 3 eigenvalues. If the degree here is 4, we should get 4. Okay. That's how. Another example, we have our B, we have our A to be equals to 4 minus 1 and 1 and 2. So you do the same way. So if you do the same way, then so you can go try this on at home. What you should get is, okay, we can do this. There's something else. So to solve this, we solve the same way. So our A minus lambda I2 here, x equals to 0. So we need to solve the same way. So for actually what we get is A minus lambda I2 equals to 4 minus lambda minus 1, 1, 2 minus lambda. So what that is what it should be. And then now we get a determinant. So to get a determinant here. So what is the determinant of 4 minus lambda minus 1, 1, 2 minus lambda? So what we get is 4 minus lambda, 2 minus lambda, and then the other one is plus 1 equals to 0. So this is our characteristic polynomial. So characteristic equation, then characteristic equation here will give us lambda square. Then the next one here is 4, and this is minus 6 lambda. And then finally, plus 9 equals to 0. So this has a polynomial of 2, so we should get 2. Now looking at these, then we can see that we can use the asymmetry. So the product is 9, and the sum is -6. So what are the two numbers in the product is 9, and the sum is 6. So it should be -3 and -3, right? So -3 and -3. So our lambda square minus 3 lambda minus 3 lambda plus 9 equals to 0. So then factoring out the common values here, lambda, so lambda minus 3 minus 3 lambda minus 3 equals to 9, equals to 0. So finally, lambda minus 3 lambda minus 3 equals to 0. Now using the zero product property, then lambda minus 3 equals to 0, lambda minus 3 equals to 0. So then lambda equals to 3, or also lambda equals to 3. So then the eigenvalue of A is lambda equals to 3 with multiplicity 2. With multiplicity. There are 2 values of 1. So you write them. The eigenvalues of A is lambda equals to 3. If there are 3 of them which are the same, then it must. Any question? So what about when you're given a 3x3? A 3x3, you do it the same way. If you're given a C here, which is A equals to -1, 0, 1, -3, 4, 1, and 0, 0, and 2. So you do the same. Okay. So our A minus lambda I3 here is the same as -1 minus lambda 0, 1, -3, 4 minus lambda 1, and then 0, 0, 2 minus lambda. 2 minus lambda. Okay. So now to get a determinant, so you use the same way that we did last time. So actually you can use one just more zeros, okay? So you can either pick this or you also or you can pick. So what is the determinant here? So our determinant of A minus lambda I3 is now equals to, we can pick this. So in this case, it is -1, okay? Okay, -1. So here it is row number 2 plus column number 2 here. And then 4 minus lambda there. And then we need to get the determinant of, we close this and that -1, negative lambda 1, and then 0, 2 minus lambda. Okay. And then finally, since this one is positive, then it is 4 minus lambda, and then determinant here, this is 0. So -1 minus lambda, 2 minus lambda. So this is our characteristic polynomial. So the equation is so easy here, since it is 4 minus lambda, -1 minus lambda, 2 minus lambda equals to what? 0. Using the zero product property, then it means 4 minus lambda equals to 0, -1 minus lambda equals to 0, and 2 minus lambda equals to 0. So then our lambda equals to 4, our lambda here equals to -1, and our lambda equals to 2. So therefore, this will now be the 1, lambda 2, and lambda 3. So those are any question after? Okay, you go try this. Number D, A equals to 5 minus 2, 3, 0, 1, 0, and then 6, 7 minus 2. We should get lambda 1 equals to 7, lambda 2 equals to 1, and lambda 3 equals to -4. So you can, so the easiest way is 5 minus lambda, 1 minus lambda, and then you come get a determinant, just close. Use this one. There is no question, then we can meet on Friday. So I'll make sure I finish the practice test for exam 3, and then I will post it before the end of Friday. So even the final exam, I'll post it next week. So I'm preparing actually the one for final exam and exam. So start from the exam. So the final exam is a comprehensive. So it's from where we started from up to where we will finish.
That's